Okay.
Um, Arpan, on this collab thing, you sent a file, I think, yesterday on Monday, and that's something we need to upload.
Yeah, so you need to upload this polychaos.ipnyv file,
Hmm.
and so you just do file, upload notebook, choose
Okay.
file,
Okay.
and this one, let's say.
Yeah, I'm just trying.
Yeah, so if you uploaded that file, you'll get something like this. Yeah, for me, it's already run once, but what you are gonna do today is trying to do polynomial chaos for power system application, where we use this chaospy library.
Hmm.
So usually if you use Python environment, then it's you install it once and it should be fine. This is just importing the library. Then in a normal uncertainty quantification, there is always three steps. First is understanding the model
Mhm.
or the design assessment criteria, and then understanding the input, or we can also say quantification of source of uncertainties, like how your input looks like, what are the uncertainties in your input, and so on. And the third thing essential is what is the quantity of interest. So what do you want as your output? So is it probability of congestion? It's a whole PDF, or you want also probability of voltage at particular nodes, or so on. So there can be a number of quantity of interest
Mhm.
which you need and can obtain through this uncertainty quantification. So in such, uncertainty quantification is to transform the input uncertainties to the uncertainties in your output, right? So yeah, so talking about the model equations, so power flow equations are the main equations for our model, which contains Kirchhoff's laws and voltage and currents bounds. So Kirchhoff's laws basically is a current laws or the voltage laws, and the voltage and current bonds basically means at particular node the voltage should be within the operational limit.
Mm.
So in this application we are using Panda Power. So let's install Panda Power to do power flow. Then once it is installed, what we are doing here is we are creating an empty network, adding a bus 1, bus 2, and then creating a line between bus 1 and bus 2, then
Mhm.
creating an external grid which is source, and adding a load, right? So this is simple power flow. We run it, uh, it's executed, and usually the output of power flow. Okay, so we created the network here and we run the power flow.
Mhm.
And running power flow is always a little bit expensive operations because it has a number of iteration to do. It doesn't take that much time, but it takes almost 13 seconds for running this simple network also. But usually, like this is a computationally what do you say, heavy computation power flow itself.
Mhm.
And usually after running the power flow, we are also interested in output, and the power flow gives the output in terms of current and voltage. So this one is the current voltage in bus 0 and bus 1, and this is
Mhm.
the current or the amount of loading
Mhm.
on the branch 1. And
Okay.
let's say we install now PV in the same bus, but half of the size. So previously the load was 1, we install PV of 0.5, we run power flow and get voltage and current, right? If you see, the current decreases by half because now there is PV in the same bus, and voltage increases. So basically having PV in the system increases the voltage of the system. So
Okay.
this is basically a deterministic power flow, and our input are load and PV generation, and the output are voltage and current. And we give one single value for the input and get a single value as an output. But assume that our load is something like this, represented by a distribution which can be anything between 0 and 4 and has different probability uh, of being different load at different time or something like that. So here we model the load as beta distribution, and the nice thing about beta distribution is, for example, if so these are the terminology: alpha, beta, lower bound and upper bound. So if alpha and beta are greater than 1, you get something curved like this. And if alpha is smaller than 1 and beta is greater than 1, you get skewed curve like this, where there is a lot of load around 0 and a little probability as you go higher. And if you put this both 0.5, means both less than 1, then you'll get something like this. It's more skewed in both end, and little bit less frequency in the middle. So what I was trying to say here is, with beta you have you can represent versatile of the distribution compared to representing it by normal distributions. But normally the load, based on a real load, the distribution of load looks something like this, which is obviously not Gaussian. And we want to do something with distribution which is very flexible, and we can do a lot of things with that. And same with the irradiance. So irradiance profile normally looks like this. It was the actual irradiance profile from Genk for a spring month of few years. And if you fit all the available irradiance data at midday, so it's not for considering whole both night and day. So it's considering only midday between 12 and 2 or something like that. And the irradiance variation something looks like this. So it's again better to represent here by beta distribution because of this versatility we can obtain, and also the possibility to have a sharp end. For example, if you assume Gaussian, the Gaussian doesn't have a definite end, so it might be sometime problem.
So one quick question upon.
Yeah.
So the polynomial chaos
Yeah.
is a post-processing thing. Is this correct?
So I think
Like,
we'll come to that. We are coming to the polynomial chaos next. So this one is about
oh,
input. So we are talking about input now. We
okay.
haven't been to the polynomial chaos yet.
But the package, like the CP dot
Yeah.
CP
So that
is
is
the
just a library. It's a
okay.
library. It hasn't done anything except just defining the distribution. So
Okay.
cp.beta define the distribution. So it
Okay.
defines the beta distribution, and here we sample that beta distribution. That's it.
Okay. And the name of it being chaos pi
Chaospy
is
it does
this.
polynomial chaos, but it also does other things with the distributions. So you can
Okay.
also do Monte Carlo or simple sampling with that.
Okay.
Okay.
So here I'm not doing any polynomial chaos yet. I'm just analyzing the input. Then
Maybe
now
it's
we
the similar to the Julia package distributions.jl. Is it something?
that
No.
is stats. There is this stats package.
Okay.
So it is more specialized just to do Monte Carlo and polynomial chaos. It doesn't do support all the distributions,
Okay.
and has some features, but not exactly have all those statistical features.
Okay. Okay.
So that's why the
Thanks.
name is chaospy, not statistics or statspy or something like that.
Okay.
Good.
So now let's come to the Monte Carlo simulation. So in Monte Carlo, what we do is, now we have the samples, right? So these are the samples of load and irradiance. What we do is we run, let's say in terms of power flow, we run power flow for each of these samples and get the output, right? So I wrote a function here which takes the load sample, irradiance sample, let's say PV size and MC samples. So PV size now is a variable here because we have a irradiance as an input. So we need to give PV size as a external input. And then what we do is we create, for each sample, we create the networks and add the load here. So basically, this is load sample and this is irradiance sample here. And we do multiply by 1000, 0.001, because irradiance was on watt and we want it everything in kilowatts. Or so, and basically these things can be done outside the loop, but in Panda Power I don't know how to do it. So that only you can change the load, you don't need to create the network again and again. But yeah, okay, this network creation part is not the time consuming one, as you have already seen before. This pp run net is the one which is consuming the time, a lot of time.
Yeah.
So I made this function, and now what I do is I run this mcppf. Okay, this function I forgot to run. So I run this function first, so this function is there. And then I run the result mcppf for 100 samples and plot the histplot or histogram of the result. So bus 1 voltage looks something like this. Uh, uh, and this is the uncertainty in the bus 1 voltage, right? So that is basically what we want to do in Monte Carlo based system, but not limited to that. We also might be want to calculate like what is the probability of over voltage on it. So what we do is we try to see how many of the samples are greater than 1.05, and then try to see what is the probability. So here the probability is around 0.13, but if you change the sample, for example, if you make a new sample for irradiance and for load, this probability will change. This is because in Monte Carlo we need a lot of samples to get very accurate results. If we rely with very less, you see it was 12% before, now I changed the samples, and then now it is 0.15. So if you want your result to converge, you need a relatively very high number of samples. Then your convergence will be faster between the two instances of Monte Carlo simulations. So this is what Monte Carlo does. And then now we also have the insight on the problem and how we solve using Monte Carlo. So now we go to the polynomial chaos. Till now we just I showed how the Monte Carlo worked. So basically polynomial chaos expansion is a way of representing uncertainties in terms of orthogonal polynomials. So I think I have slides for this. I didn't put it here, but if you remember this slide before, so I want to remind you maybe the basics of the vector geometry, where we can write anything in terms of I, j, and k. So if you have any coordinates x, y, z, we can write in terms of x, y, z is basically xi plus yj plus zk, right? And same in the Fourier transform, you have some continuous signals or periodic signals, then you can always write in terms of cosines and sines with their respective coefficients.
Yeah.
And similar here, we want to write the uncertainty in terms of those bases, orthogonal polynomial bases, and the coefficients. So instead of sine and cosine, now our basis looks something like this. X minus mu, or x square minus sigma square if it is a Gaussian distribution with mu as mean and sigma as standard deviation. Then the basis looks something like that instead of I, j, and k, or sine 2 omega, sine 3 omega, something like that. And our aim is to find the corresponding coefficient so that we can transform it into this orthogonal polynomial sequence. So the good relation here is if you do this tensor product between these polynomial bases. If they are different bases, then this inner product will be always 0. And if it is of same base, then the inner product will have some positive scalar. So in this case, it is 1 because it's not only orthogonal but also orthonormal. But the Fourier transform and this polynomial chaos, they are not orthonormal, so you get some coefficients extra product here. For example, square root of t here, or this y term or gamma term, I don't know how you call it, terms here. So these are basically the tensor products. So whenever you have to multiply this base with itself, you got these extra terms every time. So that is the only difference from the vector geometry. Otherwise, all other rules of vector geometry follows here. So coming back, now we have this, as I said, how we represent the uncertainty in terms of polynomial. And how does the polynomial look like? So it is something like that. So if it is a degree 2 polynomials of the load with beta distribution, you get something like that, 1. So it's for the defined distribution, this becomes unique. So 1 minus q naught minus something, or q naught square minus 2.2 into q naught plus 0.68 or something like that. So for the load, this is our polynomial basis. And same with if you want to go degree 3, then the polynomial basis looks something like that. So the first 3 polynomial is same, then you get a degree 3 polynomial here. Right? And same is with the load. So these are called univariate polynomials because it represents only one distribution or a load. But then if you are trying to do a problem with many variables, then if you want to take univariate polynomials, then your problem multiplies 3 times, right? You have to carry this polynomial, and then you have to carry 3 polynomials each for all the individual. Then you have to do a tensor product or something like that. Instead, it's too fast.
Yeah. No, just one question.
Yeah.
So when you're using this, command to determine the polynomials,
Yeah.
how does it know if it's a beta distribution, or because I feel if it's
We already gave the load is equals to beta, right? So if you change load equals to normal, for example, so if you say L equals to CP dot normal 1 comma 3, and then print the polynomial for L.
Yeah.
Okay, this is something, N should be capital.
Okay.
So it's different now, you see. So this was the polynomial for the beta distribution. Now for Gaussian, it's different. So these are all defined. These polynomials was in the literature for more than 60 years now, or more than that. And they were using in math just for fun. Or then it is one of the real application. Compared to in math, they just want to try this orthogonality and all these things. They don't really apply anywhere, but this is one of the application of those maths. Like Legendre created this polynomial far ago, I think. And then around 1973, this winner guy, I think, he implemented it to represent the uncertainty, and he was able to do it. So so these are something very standard, so you don't need to worry about saying. So there is nothing much you can do in creating a new orthogonal polynomials. Very standard procedure. These properties are well defined. The theorems and everything are well defined. So what we are trying to do here is trying to apply it in a power system applications.
And do I understand it correctly? The motivation to use polynomial chaos in representing our uncertainty is that we don't then have to go for Monte Carlo simulations, because then that takes up a lot of computational time and a lot of
Yeah, so we'll
samples.
come to the motivation now.
Okay.
I am just showing the process and showing the motivation along the way.
Okay.
This is great, Arpad. Yes, you
Yeah,
are
it's
very
very
good at
good way.
this.
Yeah.
Yeah.
Mhm.
So
And can I ask another question? Sorry.
yeah,
You said something about univariate and multivariate
yeah,
distributions. Does it
yeah.
mean I wanted to
No,
understand
no,
what
I'm
it
not talking
means.
about the distribution. I'm talking about multivariate orthogonal polynomials and
Okay.
univariate orthogonal polynomials, and I'm gonna show you
Mm.
them. So right now you saw only Q naught, right? So there
Hmm.
was only one variable here. So
Mm.
let's assume this was X. It's a polynomial, then you only have X in it, right?
Hmm.
But then if you have
Mhm.
irradiance, let's say it is represented by Q1 or Y, then you will have the term which is XY in your polynomial, right? Because
Mm.
now you are multiplying two terms, so there is a relationship. There will be some coefficients which
Hmm.
depends on both product of X and Y.
Yeah.
So
Okay.
either you can carry all these univariate polynomials separate and try to find the coefficient for every one of them,
Mhm.
or if you make a multivariate, then you already do this tensor product here and you try to reduce the number of coefficients you require.
Mhm.
So in this case, like if it is a second degree polynomial and if you have two uncertainties, then it is 3 times 3, so you have to carry 9 coefficients if you want to represent the system, right? But if you do a tensor product already and get a joint distribution, so what you do is we take a joint distribution of load and irradiance and make a joint polynomial expansion. So it doesn't mean anything about the joint distribution or copula or whatever. It's just taking to distribution and taking their univariate polynomials and just doing a product already. So if you
Okay.
see here, you already see like 1, Q1 minus 517. So this one is for irradiance and Q naught minus 0.657. It was here already, right? So
Mhm.
this one is for load, and you have the square term of the irradiance, and this term is the one which
Mhm.
saves your life, this q naught into q naught 1. So this is the term which is both dependent on q naught and q naught 1, and this is the square term of again the load. So now
Okay.
instead of 9 coefficient, we can be happy with only 6 coefficients, right? 6 bases and 6 coefficients.
Okay.
So yeah, for the system, we need 6 samples to find 6 coefficients. So in this, we are trying to find the quantity of interest and using and trying to find the polynomial which represents our quantity of interest, let's say. For that, we have 6 polynomial bases. So we need 6 coefficients, right? So if you want to write us quantity of interest Z equals to, in terms of these things, we need 6 coefficients. So the non-intrusive method is all about finding that 6 coefficients. And for that, we need a 6 sample, which depends on the number of polynomial, which is given by this function. So if your number of uncertainties increases or number of degrees increases, then the number of samples required increases.
Mhm.
And the samples can be created by using any rule, but in our paper we observed that using some deterministic sample rather than pseudo random generators is
Mm.
more reliable. So here we use a Sobol sample. So again, this you have this joint distribution defined. You sample this joint distribution for 7 points, and in reality how does it look is the 7 points are somewhere represented by this orange. So if you see if there is less density, then the sample is only 1, and when there is more
Mm.
density there are 2 samples
Mm.
representing, or even 3 samples representing in more denser area.
Mhm.
So if you use pseudo normal, sometimes this is not the true, because in 7 sample it can get any 7 samples. So yeah, so it's a good idea to select Sobol based sequence. And what we do now is we pass the sample. So we took 7 here just that we have one extra for verifying our result, but here I don't verify it because it was already verified. So I skip that part. But
Okay.
usually we take one extra sample if you are doing for a new system,
Hmm.
just to verify your degree you chose is fine or not, or do you have to go to the higher degree or so on.
Okay.
But here we
Arpan,
already know, yeah.
sorry, I actually am not familiar with the Sobel sample. What does that
Sobol is
mean?
they also call it quasi Monte Carlo scheme.
Okay.
So when you do pseudo-normal generation, you just randomly generated some number, right? There is no
Yeah.
specific formula. You just get one number,
Mm-hmm.
very randomly generated. But in Sobol sequence, it's more deterministic sequence.
Okay.
So for every distribution, they have a way of sampling.
Okay.
So they have a formula which samples the coefficient. So if you give the number of samples you want,
Mm-hmm.
based on that formula, it will sample the point which is well distributed or something like that.
Okay.
So this is also called quasi Monte Carlo. So if you have heard sometime quasi Monte Carlo, yeah. So this is basically what quasi Monte Carlo is. We do the deterministic sample, let's say Sobol, or there are also symbols like Halton sequence or something like that. So it doesn't do a random sampling, but it generates a sequential sampling,
Okay.
which represents that distribution very in a best way.
Okay. That makes sense.
Yeah. So this is, I think, a Russian scientist who generated around 60s or something like that, this sequence.
Okay.
But it simplifies the Monte Carlo.
Hmm.
So sometime if you need 1,000 samples from Monte Carlo, with this you can be happy with like 100 samples.
Ah. All right.
Mm.
That's pretty good.
So what we do now is we evaluate the power flow equation for the 7 samples. We have already this MCPPF. We don't need any new functions. We just rerun this MCPPF using new new samples. So SAMP was this 20 distribution. So I take SAMP0 and SAMP1, which is load and irradiance, and you get the output voltages, right?
Yeah.
So now we have the sample, we have the output. We need to find the model based on your samples and outputs and fit it in your polynomials. So what we do is we take these points, individual points, and pass it through this. So there are 6 points. Let's say if you pass it those 6 points through the set of equation, you will get a matrix 6 by 6 matrix, right?
Okay. Yeah.
And what you want to do is you want to evaluate the 6 coefficients. So let's say C1, C2, C3, C4, C5, C6 are the 6 coefficients. You have 6 evaluations and 6 by 6 matrix. So basically from that you can form 6 linear equations, right?
Yeah.
So you have the C1, phi 1, C2, phi 2, C3, phi 3, and you can write that 6 times because of the 6 by 6 matrix of the input evaluation in the polynomial, let's say. With that, we solve simple this one. So this fit regression is basically solving that 6 linear equations and finding the coefficients. So if you do this fit regression, basically we get the polynomial of the output, something like that. So this is basically our model. So model which represents our quantity of interest, which is boss voltage at boss 1. So this is the polynomial representation. And here you don't see the polynomial base anymore because it is a polynomial and simplified one already. But if you print out the coefficients, there you can really see the 6 coefficients. So we found these 6 coefficients, and if you write the 6 coefficient along with the polynomial defined, you will ultimately find this polynomial.
Okay.
And the next thing we do is we pass that a lot of samples through this polynomial. So now we have the surrogate model of our system to calculate our quantity of interest. What we do is we pass this output voltage from model is the same model voltage and new samples. So here we sample again 1000 samples. We do both Monte Carlo and we also pass through the GPC samples. And let's see how long it takes. So now it's running probabilistic power flow or Monte Carlo. So it's here now. You can see the arrow. It takes quite a while. You can take a short break to have a
Go have a coffee.
yeah.
So
Mhm.
could I ask a question?
Yeah.
It might be a silly question, but um, so as I understood, just as a summary, because because our output might depend on two distributions, we
Yeah.
found out how many quantities of interest we need, how
No,
many
no, no. How
coefficients we
many
need.
coefficients we need or that to represent a polynomial output?
Right. And we also take an extra just to validate our
Yeah, so
result.
extra is to validate saying, okay, you take a degree 2 here, is degree
Yeah.
2 sufficient or not? Or is degree 1 already sufficient for your case? Or you have to go to degree 3 or degree 4.
Right. And at the same time, we were also talking about this Sobol samples where
Yeah,
it's kind of a pseudo Monte Carlo method where
yeah,
you don't take that many samples as Monte Carlo, but
yeah.
maybe lesser, but it's a bit more accurate in terms of that it's not so random as Monte Carlo.
Yeah, it's more deterministic. So if you repeat your simulation, you'll get the same output again and again. So if you do a simulation with 100 Monte Carlo, you have seen before, right? Once you get 12% probability and another time you get 15% probability. So if you don't take sufficient sample there, you might get different results every time.
Mm.
But with Sobol sequence, you get the same result every time.
Okay.
So
And this graph we are seeing here, where we plotted the samples.
this one, yeah.
Yeah, as I understood, so the blue one is the Monte Carlo samples.
Yeah,
It's
blue
not
one
the
is the pseudo normal samples, so not a Sobol sequence.
okay, okay. Okay. So we
And
are
the
not showing
orange
the
one,
Sobol samples here.
no.
Okay, okay.
But in our paper, we also did with Sobol samples. The only thing with Sobol sample is you somehow lose the statistical property. So every time you do, you just get the deterministic value. So you
Mm,
really don't know how accurate is your results.
okay.
So for that, you have to do a lot of. You cannot repeat the sample and say like, okay, I repeat my Monte Carlo for 5 times and I got like the result very narrow. But
Hmm.
in this case, you repeat 100 times, you get the same result.
But
So you don't really.
Yeah.
if you increase your Sobel samples each time
Yeah, yeah.
and
So
your
the only
result doesn't
way is,
change,
yeah, no.
yeah,
You increase the samples, then your result changes. So if
Hmm.
you are taking 10, hundreds, 1,000, 10,000, then you can see something like converging at some point.
yeah,
But then you have to do that compared based on the lower sample and see like how is it's something like this. You have this wave, if that wave getting damped or not.
okay,
Hmm. Okay. And this formula for finding number of coefficients which we need,
Yeah,
uh, there we have this n and d. N is the
yeah,
number of uncertainties,
yeah.
and d is the degree of the polynomial. By the d, do you mean degree of the polynomial we want for one distribution, like
So it's
one?
the degree of the polynomial we give it here. So when we are creating our polynomials, do you want to
Mm,
create the polynomials of degree 2 or polynomials of degree 3? So for example, if you say degree 3, then
yeah,
you can already see the number of polynomial increase to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right?
yeah,
So if you say I want of degree 4, then it will be around 15 polynomials.
yeah. Okay.
So basically that formula is gives how many coefficient we need, and that
Yeah.
is basically because how many orthonormal or orthogonal polynomial bases are formed.
Hmm. Okay. Okay.
So this one is done. So the Monte Carlo for 10,000 samples took almost 67 seconds, and this
Mm-hmm.
one you see this a fraction of second. So even if you include the model formation time, all this fitting time, and all this thing, and also for a bigger system, we still can gain some time up to by at least by order or something like that.
Mm-hmm. And where are we comparing the solutions?
And now we are comparing the solution.
Okay.
So this is a solution of the his plot from the, so this result 1000 is from the Monte Carlo, and output voltage from the model is from let's say polynomial chaos. And if
Okay.
you see the uncertainty, it almost matches.
Yeah,
But
it's very similar.
yeah,
Hmm.
but if you take more sample, then it becomes more and more similar. So if you plot in terms of PDF or something like that, it becomes more similar.
Mm.
Because this one is only with 1000 sample. If you go to 10,000, then it will be similar. But one advantage is, if we want to go from 1000 to 10,000 here, we have to
Mm-hmm.
repeat that power flow again for 9,000 times.
Yeah.
And here it is just like you just pass it through the polynomials, right?
Yeah.
So you just add a zero here,
Mm.
sample it, and then you pass to the polynomials. It will take maybe from 0.0046 to 0. Maybe 0.046 or something like that.
Yeah.
So it is 2 times, and here it increases by 10 times or more than that.
Mm-hmm.
So yeah, but if you are happy with 100 samples, then maybe this is not a very nice choice to do it. Then Monte Carlo is fine if you have very less number of samples and your system is already converging. But if your system is not converging with less number of samples, but then it has also limitations. So if you have uncertainties more than 10, then we still are trying to figure out the numerical stability of the problem. So for 30 bus system with 10 source of uncertainty, it is still scalable.
Mm-hmm.
But if you go for a bigger system or more number of uncertainties than 10, then it still requires some effort there.
Okay. So there's sort of a window of applicability.
Yeah, so
Um,
it's like if you have like 50 uncertainty source, and then it might not be a very suitable choice, because it becomes lot uh, complex to form the model as well as to retain it. But
mm-hmm.
the other advantage is, when you are doing this Monte Carlo, you also have to store these 1000 results, right?
Mm-hmm.
So for each nodes, if you don't even need the voltage of bus 0, or if you don't need the branch current, you still need to calculate those and retain those. Or even if you don't retain it, you need to calculate it. Here you store it in the form of polynomial. So basically these 6 coefficients and these orthogonal polynomials will represent your model. You don't need to store 1000 or 10,000 data points. And whenever you need, you just sample the inputs and pass it through the model. When you don't need, you don't do anything with that.
Mm-hmm.
So that is the application. And as we said, degree 2 was found enough for our power flow calculation. But if the application is different, it might not be true.
Mm-hmm.
And here the uncertain variables are assumed to be independent. So load and PV, they are assumed to be independent.
Mm-hmm.
So you are, if you have a house, you are assuming that a load, your consumption of the load is separate, your PV is separate, and they are independent. But if these things
Yeah.
are dependent on some other variables, let's say if you want to model the uncertainty of temperature, and your loads are dependent on that, it's still fine, because you have one uncertainty. But if you have something like uh, a dependent load or something like that, which depends on another load, and you want to model it independently, maybe it's not a good choice, but there are still some options to do that, but it increases the complexity of the problem.
Mm-hmm.
Uh, so yeah, correlated thing cannot be done, but if the correlation is perfect, then we can do it. So if it is a linear correlation, so if you are quite sure that load 1 is 0.8 of load 2,
Mm-hmm.
then you just represent it by one uncertainty and provide the factor 0.8 for another load, then it is fine.
Mm.
But if you have this non-linear collinearity where the load depends in some 0.8x plus 3 or something like that, then you need a higher order degree or something like that.
Okay.
So, and at the time of we were working, discrete variables were not supported, so all those distributions would be continuous, like beta or normal or gamma or uniform or something like that. So if it is a known continuous distribution, it was supported. They are now trying to do for discrete variables, I believe, but it's till now, I don't think it's supported in this package.
Mm.
So yeah, so what we did here was non-intrusive model, and we did it for power flow because power flow is more, you don't try to play around with the constants. So you can, it's something like learning a power flow, right? This non-intrusive one is, so what you did was you had a quantity of interest. You try to learn the model based on few samples. So it's not actually a machine learning based method because we don't have thousands of samples and we try to fit the model into it. But we have our physics based model where we try to put few samples and try to regenerate that model in a simpler form. So it's more analytical method rather than machine learning. But then Martha also pointed out something like a state vector machine, state vector SPM, and some other guys pointed out even like it might be even like a FEM where you try to convert the dimension of the problem from your infinite dimensional uncertain space to finite dimensional coefficients.
Mm.
So this one is non-intrusive PCE. As you see, we took these blue samples, which was orange on the previous curve. We did power flow evaluation on that and form a surrogate model, which was a polynomial, and we passed these samples through the polynomials. And if it was a Monte Carlo, then we have to pass all these red samples through this power flow evaluation. So this is the gain in the time we obtain here to obtain the quantity of interest.
Okay.
What this, as I said, doesn't solve all the problem. It solves the power flow type of problem. But if you have some constraint which you have to optimize or so on inside the problem, considering uncertainties, then there is a different variant of polynomial chaos, which is called intrusive polynomial chaos. So here, what we do is we have to reformulate the physics-based equations in terms of the coefficients of the orthogonal polynomial basis using Galerkin position. What do you mean by this? Is here we were writing output y in terms of orthogonal polynomials and trying to find the coefficients. In intrusive PC, what we do is we write the input uncertainty in terms of those polynomials. So for our case, we had load and irradiance. So we created that multivariate polynomials. And what we want to do is we want to write that input in terms of that polynomials. So here, this one were the polynomials, if you remember. So we had these 6 polynomials. So then the random variable x and y representing load and irradiance, we can write in terms of using, basically here, what we use is the central limit theorem, where for any distribution, the mean and standard deviation it starts conversing if you take sufficiently large number of samples.
Yeah.
So based on that, we can represent any such distribution using 2 coefficients only. So
Okay.
that is also again a theory proven around 70s or 80s and used on math a lot. and we are using it here. So it's not something I invented. It's already there in the mathematics.
Mm-hmm.
So basically what we can do is we can represent, so we have these 6 coefficients. We don't need all of these 6 coefficients to represent the load. So we just need the first coefficient, which is mean of the load sample,
Mm-hmm.
and let's say third coefficient, which is the standard deviation of load samples. Third coefficient, because this third polynomial is about load. So load is dependent on the polynomial, which is load, right?
Mm-hmm.
And for y is irradiance. So for irradiance, what we do is we take the first coefficient as the mean of the irradiance sample, and the second coefficient as the standard deviation of irradiance sample. So here the second polynomial is the irradiance, so the second coefficient should be about the irradiance.
Okay.
So in this case, you have to be very careful about this order of these polynomials. So in the intrusive one, you didn't care because you were just
Mm-hmm.
concerned about Q1 and Q0, and at the end it take care of itself. But now we are trying to redefine these coefficients ourselves
Mm-hmm.
manually using central limit theorem. So we have to be very careful about the order of the polynomial. So in different, if you use different toolbox, they sometimes screw with this order. For
Okay.
example, in Julia, the order is different. So in
Mm-hmm.
Julia, it starts from Q0 and then for Q1. Here it is reverse. So these are like, there are 3 or 4 types of writing these polynomials. So you have to be careful while creating these coefficients for the x and y, or basically for the load and irradiance.
Okay.
And what we do now is we have to transpose or propagate these coefficients through power flow equations. And there are 2 mathematical operations. One is addition and another is multiplication, right? Most of our power flow equations are basically addition of the linear terms or the
Mm-hmm.
multiplication of the quadratic terms. So if it is addition, it is simple. Your coefficient of, if z equals to x plus y is the equation, then your coefficient will also be the just sum.
Okay.
So for example, if it is a Kirchhoff's current law, I1 equals to I2, or I1 plus I2 plus I3 equals to 0, then you just write the same equation for each coefficient. So there are 6 coefficients. So you write 6 deterministic linear equation for all those 6 coefficients. But the tricky part is whenever there comes the multiplication, we of course multiply the coefficients.
Mm-hmm.
But then trickier part here is this m. So this m comes from, if you remember when I said there is a inner product, when you do
Mm-hmm.
the inner product, if it is not orthonormal or normal, there is some variable y.
Yes.
So when it is not orthonormal, so it has some variable y, right? So this
Mm-hmm.
m is basically that variable which is pre-calculated, or that constant which is pre-calculated. It's not a variable, it's a constant. So
Mm-hmm.
imagine we are dealing with a coefficient, but we need to remember that there is also the basis, polynomial basis, right?
Mm-hmm.
In this case, we could forget those polynomial bases because there was no inner product between them.
Mm-hmm.
It was just addition. So addition, you can just eliminate the polynomials. But here you are doing the inner products, means you cannot forget the inner product of the orthogonal basis.
Mm-hmm.
So that's why we introduced this m terms. But the good news is this m is basically can be calculated beforehand when we know this joint distribution, the input distribution. We
Mm-hmm.
can calculate it like this. It's basically the inner product,
Okay.
and inner product is nothing, is some integral, or it can be defined in different way. In this case, inner product is the integral add some to it dx. So it's integral from 0 minus 1 to 1 or something like that. Or assume that in a vector product, inner product is like x1 x2 plus y1, y2, right? If you have like x1i plus y1j and x2i plus y2j, what is the inner product? It's x1 x2 plus y1 y2, something like that. So here you take the sum of those x1 y1 plus x2 x1 yeah, x1 y1 plus x1 x2 y2 plus something like that, and then multiply with this tensor product to have that external factor, which we don't need in vector geometry because they were orthonormal. And
Okay.
with these two operations, we can do the non-intrusive intrusive polynomial chaos expansion. And if you want to do the chance constraint optimization using that, we have a very interesting feature here, which makes you do this chance constraint optimization. The first coefficient always represents the mean of that uncertain random variable or stochastic variable, and the square of the remaining variable represents the variance. So you can use these two features. So now you rewrote the, let's say you rewrote all those physical equation, you do Galerkin projection, and you got the output. So you basically get the coefficients of the output, and for that coefficient, the first coefficient is always the mean of that output, and the sum of the square of the remaining coefficient is the variance.
Okay.
And stochastic bound eta is usually implemented like this. So probability of x greater than or equals to x mean is greater than equals to 1 minus eta, or x less than this is always greater than 1 minus eta, right? So this is how probabilistic chance constraint is implemented. This can never be kept in a OPF problem because it won't really work. It's neither linear nor convex. So what you can do, you can convexify by reformulating it in terms of this mean plus minus lambda into square deviation. So basically, it will give the value of your C bar condition. We call it C bar. So conditional value at risk or something like that. So we try to minimize or maximize that. And basically, this lambda is the tuning factor, which determines your chance constraint. So for example, if it is 1.65, then it is equivalent to the chance constraint of let's say how much 1.65 is 5%, or 1.03 is equivalent to 10% chance constraint or something like that. So based on this lambda, you can basically tune your chance constraint limit, whether you want 5% eta as 5 or percent, or 10% or 15%.
And
So
lambda is kind of, it's a function. It's not a
lambda
parameter.
is a value.
It's just a constant.
Yeah, it's a constant.
Okay.
So that you can tune according to what is the chance constraint you want in your problem. Do you want the chance constraint of 5%, 10%, or 15%? According to that, you try to tune that.
Okay.
So now I'm going to show you the Boss constraint. So it's in a IV formulation, so current and voltage formulation. And these are the, what do you call it? Kirchhoff's current law, as I said, is a linear, right? Sum of the current and sum of the current in the branch and sum of the current from the units should be equals to 0. And these are the shunts, I think. And same with for the imaginary currents. So these two are a linear constant, and if you implement it in a Galerkin projection sense, you do nothing, you just replicate it for k times. K is basically the coefficients. So if you have 6 coefficients, you rewrite this equation for 6 times. And this one is the tricky part where there is this quadratic terms, right? It's a voltage square, which is the square of the real and imaginary parts. And this one is tricky part. So we need a multiplication terms here. So what we do is we bring a auxiliary variable called W, which is a square voltage, and which is represent as sum of these tensor products basically. And multiplied by m, which is the factor we got it from the tensor product of the polynomials.
Yeah.
So this m changes for every k1, k2, and for every k1 and k2, m is different. And finally, we have this chance constant. So instead of binding the voltage itself, we don't bind the actual individual voltage, but in this square of the voltage, we apply the chance constant saying, okay, this square of voltage uh, uh, can go up to 5% away from the limit or something like that. So, and these are all linear and, and not linear quadratic, but it's still, I think, equivalent to the non-linear AC powerful problem. So yeah, basically we reformulate all the constant like this to get the actual OPF problem. So this is the end of the theory here. Then I'll go for your questions. Then
Arpan,
otherwise I'll also.
just one question, Arpan. In the chance constraint, when we write it mathematically, we have this tolerance, right? And you were telling at some point how it gets reformulated in this equation. So is the lambda then a function of that tolerance? No.
Yeah, but usually we take it definite. So if you have so this lambda is generated assuming that your output is nearly looks like Gaussian.
Okay.
So if you have a Gaussian distribution, then you can always reformulate your Gaussian distribution in terms of mu plus lambda into variance. And if your lambda is tuned to 1.65, then this gives to that particular
Okay.
Did he freeze for you, Vaishali?
Yeah, maybe
No?
some network issue. For me too.
Okay. Yeah.
Normally it's me, but
It's me too. Well, in this sense, at least. Yeah. But he looks handsome frozen on the picture right now.
yeah, I think maybe it's kind of that he can just switch back when the internet connection restores or something.
Yeah.
Yeah, I think my internet got disconnected. But you were talking about lambda. So basically, if it is a Gaussian distribution, then mu plus 1.65 into standard deviation represents that point where your PDF is has 95% of the area covered.
Okay. Yeah.
How are you coming at 1.65? I was.
Yeah, that is just assuming the Gaussian distribution if you take the enough samples. So it's they call it, I don't know what they call it, but it's you can take the inverse of a Gaussian to find that lambda.
Okay.
So I don't really know the operations, but if you take like 1,000 samples and then of a normal distribution, and if you do mu plus 1.65 into standard deviation, then you will get a number or a point below which there will be 95% of the probability, and above that there will be 5% probability. So they call it something inverse CDF or inverse. I don't know what they call it mathematically, but that is something you obtain assuming it's a Gaussian. So that's one thing I
Hmm.
also did in one of the papers. So if you are taking a lot of beta distribution and they are very much skewed, then that lambda value needs to be tuned according to your output. So you need to do 2 times the OPF. First times to find initial statement, initial state, not statement, initial estimate of the your chance constraint violation. And second time you try to tune lambda to make it more accurate to 5%. So this is not very like exact representation, but I think this is better than what we have for non-Gaussian distribution.
Okay.
So this one is about the theory, and I want to show you how it looks. So if you install this stochastic power model package, I think Khan gave the Pluto notebook. Unfortunately, I cannot run that in my system. It runs, but it keeps on running.
Okay.
So I'm showing you the main package where there is this example called case 5 SPM. So if you just add this stochastic power models package and then look on the examples, then there will be this case 5 SPM. So basically here, your input will be always like, you can give the degree, you can give the auxiliary variable, which is always true. The auxiliary variable means something like W we introduced before. That's the auxiliary variable. So there is also a way with we can do without this auxiliary variable, but for now, I think we have proven that with auxiliary variable, it's better.
Okay.
So we prefer this always true. Then you can put the name of the case here, and then just use mat power file. Let's say you have a file, and then you parse it, and you just run IVR and ACR. So while parsing, so the file is little bit different than original one. So if you want to see how it looks like, uh, case 5 examples. It should be in test, data, mat power, so case 5 SPM. So it's the original file, but then what we add extra is the stochastic data. So basically we give the input uncertainty beforehand in the file itself manually. So what are the uncertainties in the system? So here we have two uncertainties, beta and gamma. We give this lambda Cmax externally. So here we are giving 1.0364. So that means 10% of things. And that's it. I think we also might need to give, yeah, for the generator also we need to give extra this lambda p mean, lambda p max. And for voltage also, I think for voltage also we need to give the lambda v mean and lambda v max.
Okay.
But I think there is a function somewhere here which does that for you already. So it should be somewhere in the util. Let me see, where is util src, util data. So here you already have this. Wait, this is too big. So you have this extend MATLAB file data, which parse the path and also add those distributions. So lambda in the bus and everything, and generator things as well as branch things, and make a new file at the end. So from here you can change this if you want 1.3 to 1.65. You can change here. Now it has been done manually. but it is something you build for one time and it's done, right? But you can also, maybe Khan is attempting to make it more automatic, so maybe in future you will have an automated way of making a new MATLAB file or MATPAR file based on the existing file. And then also you also need to say like which distribution ID your boss should be. So if you remember, there were two distribution ID, beta and normal. So here you have to assign like which boss will get which distribution somewhere. So yeah, this is about making the file, and once your file is ready, I think Khan also shared a PPT about making the file. I think there he also mentioned, I think the file he sent, there is also a PPT where it is also mentioned how to uh, convert the MATPAR file to the file accepted by this. So basically you have to put this lambda terms, distribution terms, and also allocate which load is getting which distribution. Once you have that, just you run IVR. Okay, solve SOP IVF not defined. Why is it saying not defined? It was running before. I don't know why it's not running now. It was running just before I checked. I can maybe restart. I think I didn't run all of the folder. So this is how you run, and if you see inside this problem, then I can show you how those things were implemented. For example, I go to IV formulation. So it's built like a power models. So you have those variables, everything. So you define variables for everyone here. It's nothing much different. The only difference is, for example, this constraint GP. So GP means Galerkin projection. And this was the thing we saw, right? Magnitude square. So if you go to the definition, so this is how we implement the Galerkin projection. So this T2, T3, this is basically, if you remember, M was this, right? Tensor product of K1, K2, K, 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 right? So if you see it here, it's basically M is this T3, N1 minus 1, N2 minus 1, N minus 1 upon T2 get N1 minus 1, N1 minus N1.
Okay.
So these things are already pre-calculated. So whenever you form, so if you give the distribution, we already pre-calculate this, so you don't need to worry about this. The only thing is you implement your product, something like this. So you have BR square plus BI square. Now you implement it as a product of BR N1 into BR N2 plus BI N1 into BI N2 for all those coefficients. So basically for all K. So N1, so this creates all those coefficients for BR and BI, and we take the tensor products over there. This is somehow not running for me. I think I screwed something. A lot of I'm running it from the wrong place. But
WIDs.
yeah,
Yeah.
normally it should work. I think I changed something somewhere because it is good. It's getting to power model distribution. Why it is going to power model distribution?
Yeah.
Maybe
So it
the
was,
directory
Yeah, I think I
That's
screwed because
different.
I think Power Model is also open here, so a lot of things are open. So maybe this one should run then.
That NWID's error I've seen before,
Yeah. So
not with this one exactly,
it's
but
just conflicting with, I think, 2 or 3 things I am opening here.
mm,
Yeah, I really don't know what is happening. But usually, if you open it fresh,
Mm.
I can do, I think, save all and restart. Uh, yeah, I was doing multiple things this morning, so I think it's already messed up. It's better to remove these things, I think. But usually it works.
Mm.
mhm.
And what you can also do is print the summary as in normal IVR thing, but then you can also see the coefficients here. So if you have a PG, you can see the coefficients, and then also you can sample those coefficients to get the output, something like this. If so, this was I think just before I talked to you, I created this sample, but it decided not to work now. But
Yeah.
you'll get something samples like this based on that, so, or something like this. So this was the sample I created for these 3 PM in bus 1, 2, and 3 for simple bus 5 bus case. So your output will be in terms of the sample. So basically, output will be in terms of the coefficients, and from that coefficients, you can sample your output, how the distribution looks like.
Mm.
Yeah, and in implementation, yeah, it's a bit easy to say and difficult to do because I'm still struggling. So this morning I was trying to struggle with a 3-phase stochastic power model. It satisfies everything, but it's still there is some problem in there. So it's sometimes looks easy but gets complicated. But the basic trick is something like that. So if it is, you have to write all your equation. If it is linear equation, do nothing with it. You just replicate it for n times. If it is a non-linear equation, then you have to
Mm.
write the Galerkin projection for that. And if it has some crazy things like square roots or something like that, then that we cannot do Galerkin projection for that. We have to reformulate in something of which we can do Galerkin projection.
Mm.
That's it from my side. If you have some questions, a lot
That
of
was
questions,
excellent,
or
Arpan. Yeah, really, really, really good. Um,
then
it,
I'll
it
stop
is
recording. I
okay.
think that is the end of the tutorial, and then we can discuss. Ah,
Okay.
fuck. It's not
And
recorded.
oh, maybe just when you